Hey everybody, it's Brandon from STEM Tutor Club, and today we're going to go over this exponent rule right here, which is called the quotient rule, or sometimes called the quotient of powers rule. So we'll show a couple examples of how it works and then why it works. So stick around for that. Okay, so first we're going to try to calculate 2 to the fifth power divided by 2 to the third power. And we're going to do it the hard way and with the formula. So the hard way, so 2 to the fifth power, and you could calculate that out in a calculator, 2 times 2 times 2 times 2 times 2. So 2 times itself 5 times, that'll be 32. And then 2 to the third power, 2 times 2 times 2 will be 8. And then 32 divided by 8 will be 4. So it's not that hard, but the formula gives us a faster way to do it. So in this case, the way that we're going to look at this is that 2, 2 will be the x in this formula. So we say that x is equal to 2. And then, let me find another color, m will be 5. So we'll say m is 5. And then we'll say, let me get a better color. So then we'll say that n is equal to 3. And if we have these three variables, then according to this exponent property, we should be able to rewrite this entire thing as x, which is 2, and then raised to the power 5 minus 3. So 5 minus 3. And then for this problem, it actually looks like this is more work, but in general, it's actually a lot less work once you get used to it. But here, you can see that 5 minus 3 will be 2 to the second power, and then 2 to the second power is equal to 4. So you see that we get the same answer both ways. From this, like I said, from this one, it might not be clear why the formula is actually easier than just calculating them out the hard way. But from the next example, that'll become more clear. So in this example, we're actually dealing with gigantic numbers that are basically impossible to calculate by hand. So 3 to the 13th power would be 3 times 3 times 3 times itself 13 times in total, which just gives you a massive number. And that number, it turns out, is actually equal to, I'm going to pop it in here from the calculator. So 3 to the 13th power is equal to 100 or 1,594,333. So a gigantic number. And then we have something very similar with 3 to the 10th power. So for example, 3 to the 10th power is also a gigantic number, 59,049. So if you actually calculate these out, and again, you basically must have a calculator to do it because it's too hard otherwise to do by hand. So we'll have 159 or 1,594,323 divided by 59,049. And now if this answer jumps out at you, then you're better at this than I am, but basically you have to calculate this in a as well with a calculator. And once you do that, you'll find that it's actually equal to 27. So if you divide this gigantic number by this slightly less gigantic number, you will get 27. However, with the formula, things are a lot easier. So in this case, x will be 3, m will be 13, and n will be 10. Therefore, we can rewrite this entire thing as just 3 raised to the power 13 minus 10, which is 3 raised to the third power. 13 minus 10 is 3. And then you can see that we would end up with 27. So here, this is where you can see that the formula is actually a lot less work than the alternative, especially when the numbers get big. And now here we want to try to understand why that worked for each of the two. And the best way to understand why this formula works for every number, besides 0, of course, because you can't have division by 0 in the denominator, but as long as you don't have x set equal to 0, for everything else, this will work, this formula, for all other possible combinations of numbers. But the best way to understand why it works is to actually list out what the numerator and denominator equal here based on the properties of exponents. So for example, 2 to the fifth power, what does that mean? Without actually calculating it, basically what it means is 2 times itself 5 times. So we have basically 5 2's in the numerator being multiplied by themselves. And then in the denominator, we have 3 of them. And if we do that, you should actually notice something interesting. It's that whenever we have something in the numerator and in the denominator, we could actually simplify the fraction by crossing it out. So in other words, this 2 in the denominator here cancels out with this 2 in the numerator. And then same here, and then same here. And you can see that after we do that, we would be left with 2 2's in the numerator being multiplied by one another. And then 2 times 2 is obviously equal to 4. So what did we really do here? You can see why the formula comes through, because the whole formula was to say that we should basically do 2 raised to the power 5 minus 3. The reason that we're doing the 5 minus 3 here is that represents these numbers being crossed out. So we don't actually care about how many total numbers are in the numerator versus how many total are in the denominator. All we really care about is how many more are in the numerator than the denominator, because all the other ones cancel out. So that's the basic idea. That's why this formula works the way it does. And you can see that it's also true over here when we're doing 3 raised to the 13th power divided by 3 to the 10th power. If you work this out, so 3, I'm going to write it out 13 times. So that's 3 times 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 13 in the numerator, and now I'll do 10 in the denominator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So a lot of 3's in the numerator and a lot in the denominator. However, according to the same logic, we really don't care how many total there are, because most of them, the vast majority of them, are going to cancel out. So we'll have 3 raised to the power 13 minus 10, and you can see here 13 minus 10 really corresponds to these canceling out. So that and that, that and that, that, and then continuing this process, we just keep taking 1 out of the numerator and 1 out of the denominator until we're finally left with 3, which is exactly what you would expect here. So we're going to end up with 3 times 3 times 3, which is by definition 3 to the third power, which is finally equal to 27. So that's the general idea. That's why these formulas work with actual numbers involved. Now let me explain how it works when things are a little bit more abstract. So this time, instead of dealing with actual numbers like we did in the last case, we're going to deal with basically everything as a variable. So the way I'll represent this is, I have x times x times x times dot 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 all the way up to x, and the way we represent with how many x's we have is we'll say this. So we have m x's, whatever m is. Again, we have no idea when we're doing it in general. And then we can do something similar idea on the bottom. So this is just very general, same idea as above though. And you can see that basically with the same logic, even though we don't know exactly what m and exactly what n are, we can tell that we should end up with x to the power m minus n afterwards. And then remember this, the entire time this was equal to that. So this is the same kind of idea that we did before. Basically, if we have one x in the numerator but also one in the denominator, well, that pair cancels out and it's irrelevant. And if we just do that until we run out on the denominator, then whatever we're left with in the numerator, well, then we could just treat it as that. And we're really just simplifying fractions is another way to look at it. So hopefully that made it clear why this formula is the way it is. And now before we go, I want to throw a little bit of a curveball that kind of leads to an interesting question when we're talking about exponent properties. So here what I want to calculate is 2 to the third power divided by 2 to the sixth power. So here you can see that the sixth power is higher than the third. So now the denominator is actually going to be greater than the numerator. And we're going to try to see what happens. Now, if we use this exponent property, then the rules are very simple. We know that x would be 2 in this case, 3 would be m, and 6 would be n. So if we write 2 to the third power over 2 to the sixth power, then according to our formula, that should be 2 to the 3 minus 6 power. What is 3 minus 6? Negative 3. So this whole thing should be 2 to the negative third power. However, we have no idea what 2 to the negative third power means. The exponent is negative. We've never seen that before. So how can we make sense of it? Well, the way to make sense of it is to actually do what we did before and actually write the whole thing out. So if we write the whole thing out, then we can say that 2 to the third over 2 to the sixth, if we really write that out, is equal to 2 times 2 times 2, 3 times in the numerator, and then 2 times 2 times 2 times 2 times 2 times 2, 6 times in the denominator. And we actually cross these out, so that crosses with that, what are we left with? What we're really left with, if you see, is 1 divided by 2 times 2 times 2. So we're left with 3 2's, but this time they're in the denominator instead of the numerator. So this, if you think about it, is by definition equal to 1 divided by 2 to the third power. It's just that 2 is in the denominator instead of the numerator, like we're used to. And that actually equals 8 in this case, so 2 to the third is 8. So the final answer is 1/8, but before actually even going there, we see something kind of interesting that apparently, according to the way that we've defined our property here, this sort of makes it seem like 2 to the negative third has to be equal to 1 divided by 2 to the positive third. And this actually is the definition of negative exponents in general, which is something that we'll go over in a lot more detail right now. So be sure to stick around for that.